Hey everybody, this is a quick podcast on kinetics, and this actually deals with the rate of reactions, how fast reactants are disappearing and how fast products are appearing. Not thermodynamics or anything like that, but how fast things are happening. And so if you look, this is a typical graph that you might see for a reaction. And if you notice, there's red lines and blue lines, and the red lines specifically deal with the reactants. And those reactants are disappearing. And I don't want that color. Okay. Now, if you look at time 0, what's true? My reactants, I have some. What's happening to them? They're disappearing. They're not disappearing at an equal rate. They end up evening off over here, which is equilibrium. That's a different chapter. But if you look, they're in a ratio of 1 to 2. Okay, and so this is one of the times that you can look at coefficients in a reaction are here and in a different part of rate, and then also in mechanisms. So you can look at this as a stoichiometric relationship that for every 2 moles of ICl that goes away, right, 2 moles of ICl, 1 mole of H2 disappears. So this is disappearing half as fast. This is disappearing twice as fast. Now, on the flip side, what's true? You have products, and on this graph, the products are blue, aren't they? And so if you notice at time 0, I have none of these, and something's appearing twice as fast as this right here. So what is this twice as fast? Oh look, it's hydrochloric acid, and this is iodine. And if you look in the coefficients in your equation, hydrochloric acid is appearing twice as fast as I2. And so you can use these stoichiometric relationships to go ahead and figure out some problems, right? So there's looking at a graph and be able to read it. And then there's also, that's rate, okay, rate of appearance and disappearance. But there's also looking at a chart like this. So if you notice through this whole chapter, a lot of the things that we're talking about are simple. You just have to know when to do them. So we were talking about rate right there, right? How fast something's appearing and disappearing. And so you look right here, this is rate. Rate has to do with change of something over change in time. If I look at rate of how fast a runner is running, or how fast a fish is swimming, or how fast a car is disappearing into the sunset, I'm looking at change in miles per hour, right, or meters per second. So here we're looking at change in concentration over change in time. And here specifically, I know nothing about my products. I can't tell you anything about them right now, but I can tell you about my reactants. I can tell you at time 0 in this chart that I have 1.46 moles per liter. And at time 1986, I have 0.43. This is kind of blurry, I know, sorry. What happened? Tick-tock, time went by. What happened to my molarity? It went down. How come? Because it's being used up. And I could find out how fast things are going away and how fast things are appearing based on charts like this. And we'll do that in a second. Okay, but this is what you would see when you talk about rate. Time and concentration. And again, we'll do a problem like that in a second. Now, what is rate law? Well, there's 2 kinds of rate law. There's a differential rate law or differentiated rate law. Okay, you can fool around with this word all you want to, or integrated rate law. What does differential and integration have to do with anything? Well, that's calculus, and so this class is not a calculus-based class. In college, you won't take a calculus-based class for chemistry. They just did magical math behind the scenes, okay? And a differential rate law, you deal with information that's in a chart in front of you right here. If you notice, what do you see? You see experiment 1, 2, and 3. You see rates. You see information about reactants. These are my reactants right here. That's a reactant here, and that's a reactant here. You change the concentrations of them and you compare them. That's very different than the information you see in this chart. This is time and concentration, which is rate. In this chart, it's experiment 1, experiment 2, and 3. That's rate law. Okay? Now, in integrated rate law, these are the equations. They will be given to you. That's going to be a different podcast. I want it to be completely different and separate from what we're doing. You see this information, which you saw with rate, and I want you to find some information that you can't find unless you use your calculator and you use a linear regression And that will be in a different podcast. I need to find a good online scientific calculator that I can show you how to do this on. Okay? So, again, differential rate law, integrated rate law, and there's rate. So let's talk about rate. So I'm going to go ahead and find out the rate of disappearance, how fast this N2O5 is going away, okay, between, because I'm going to tell you in between where, because remember that graph before we looked at? That graph we looked at, things didn't disappear at equal rates, did they? Okay. So, if you look here, right? Can you wrap it back here? This graph, things disappeared in between. Here it was faster and here it's slower. So I need to be very specific about the time frame that I give you. So specifically between 1,986 seconds and 753 seconds. Between this time period, how fast are things going away? Okay, typically reactants are here. So how do you do this? Well, it's change in concentration over change in time. So my concentration here, I don't know if you can read it really well, is 0.43, and that's molarity, okay, moles per liter, minus, right here, it's 0.89, I can put a 0 out front, molarity. That's my change in concentration, or my change in time. Remember, this is final minus initial, isn't it? That's how you find things, okay? Except for bond energy. So this is seconds, and this is 753 seconds. And when I do my math, I get 0.000373, or the rate of disappearance of N2O5 between 1,986 seconds and 753 seconds is equal to 3.73 times 10 to the minus 4th molarity per second. That's because this is molarity per second. It's going away that fast. Between this time period, it's disappearing with that many moles per liter per second. Okay? So that's how you figure out rate, again, with the information in this chart. All right, now, what if I gave you this information? Okay, I didn't have a chart, but I gave you a fact that the rate of disappearance for H2 in that previous graph is 3.0 molarity per second. Okay, I don't have to tell you where and when it is, but let's just say between a certain time period and a certain time period. In other words, someone already did that math for you. And from this, you want to find the rate of disappearance of the other reactant. Here's my other reactant. So I want to find how fast this is going away. And the rate of appearance of both my products. So, how fast is iodine chloride, iodine monochloride, how fast is it going away? Well, I know that my hydrogen is disappearing with the rate of this many moles per liter per second. Okay? And I'm going to go ahead and use my stoichiometry. So here's a time when I can look at my coefficients. And for every, and this is hydrogen, for every 1 mole of hydrogen that disappears, I make 2 moles of ICl. Look what happens. My moles of hydrogen cancel. I'm left with moles of ICl. And it makes sense that it is disappearing at a rate of 6 molarity per second. Because of what reason? This is going away twice as fast as this is. So it's disappearing at a rate of 6.0 molarity per second for ICl. Disappears. Okay, now, sometimes you'll see, instead of the word disappears, you'll see this, that it has a negative rate. And all that negative rate means is that it is disappearing. It's going away. It's negative. All right? So let's go ahead and find out about iodine and hydrochloric acid there in my products. And I know that hydrogen, okay, 1 mole, 3 malonite. Sorry, here you go. All right? So 3 molar per second. of hydrogen is disappearing. And for every 1 mole of H2 that disappears, 1 mole of I2 appears. So what's that mean? As fast as hydrogen's going away, iodine is being produced. So iodine is appearing at a positive rate. That's the rate of appearance. So you can either say it's positive or you can say it's appearing. And this is I2. Okay, now if we go ahead and just use this same format and fill in the values for HCl, I'm going to put 2 moles of HCl up here. Because for every 1 mole of hydrogen that goes away, 2 moles of HCl are produced. And so hydrochloric acid appears at a rate of 6.0 molarity per second is appearing, or it's positive, for HCl. Okay, so that's one time you look at the